max player who try to maximize the utility and the selected action by the max operator is related to the highest min-max value. Min-max value is the name of the function that is used in our discussion. And after the max player, the min player try to select another action with respect to the lowest utility, because the min player tries to minimize the max player utility. And we explore the tree by starting from a node and try to check the successors of the current state. In the blue function, the max player call maximization over the value of the child, and for the min player we call min operator over the successors of the current state. The process is done in DFS manner. DFS manner is simple, but for searching the gaming tree, the number of nodes in DFS is very, very great. But for finding the optimal action, we need to check the DFS for getting the best action for the game. This is the code of our process we discussed previously. As you see in the blue box, we initialize with v equal to minus infinity. We have a loop. This loop is over on successor of the state, because this node is max player. We call max operator over the current v and the output of the child. The child are min player. Because of that, min value function is called over the successor. And when we have a better value from the min value functions, we update the value of v. Similarly, for the red box, we started with v equal to positive infinity, and in the loop we check all of the successor, because the red box is defined for the min player. We call min operator, and in the min operator we compare the current value v and the output of the successor. The output of the successor is defined by max value of the successor, because the child of any min player is max player. We call max value over it. And this process continues until receiving the best action. It is a unique implementation of Mike Smith's implementation. Do you have any problem? Do you have any ambiguity? No one? Okay. If we ask about the performance of maximum property, we should consider different concepts. One of the important concepts is optimality. For the optimality, because we check the entire of the tree, we can say that if the players are perfect, we can find the optimal solution by hours. But it depends on the DFS search. If the players are not perfect, again, we can use our algorithm, but our algorithm needs to check entire of the tree. That is possible for some simple simple games, for example, tic-tac-toe, but it is not possible to implement for larger scale problems. For larger scale problems, more intelligence is needed. And about the complexity, because we use DFS, the complexity is similar to DFS. As you remember, the time complexity of DFS is B is the branching factor, shows the number of children for any node, and M is the height. And the space complexity is big O, B cross N. But as you see, for larger scale problems, for example, chess, the complexity is very, very high, and it is infeasible to check entire of the tree. Now, in this class, we consider a new attempt to improve the quality of min-max algorithm in practice. In practice, instead of using the pure min-max algorithm, we need to consider some improvement to decrease the amount of the necessary computation for checking the tree. Tree depends on the depth. Thus, by limiting on the depth, it is possible to stop earlier and decrease the amount of the computation. Because of that, we need to find some heuristic for decreasing the depth of the game tree. And also, it is possible to propose some heuristic for evaluating the nodes before terminal nodes. It is very, very important to estimate the amount of the utility earlier. And because of that, we can define some imperfect guess instead of the exact utility to compare the results and compare the utility of nodes. But this new attempt causes a new problem, namely horizon effect. Please pay attention to the horizon effect. To present the horizon effect, consider the chess. As you see, by losing a queen, there is a great problem for any player, and because of that, checking the states to save the queen is very, very important. But based on some horizon, you lost the necessary information to estimate the losing a queen. To explain better, I define the horizon effect as a drawback of depth limited search. In the depth limited search, for example, in this tree, you limit your attention to, for example, level 0 and level 1. But maybe in the next level, for example, level 2, there is another node, for example, J, that is beyond the limited search, limits your vision about understanding the status of J. Because of that, if there is an catastrophic event in the tree just after of the level that you stop the search, the algorithm remains unaware of it and may choose a path that connects to it in the worst case. And because of that, limitation of the vision causes a great drawback in your searching process. This is horizon effect. In the game algorithm, you should consider horizon effect in your implementation. Now, we need to propose some extension of the searching algorithm for adversarial problems with respect to restricted resources. For the restricted process, the best option is pruning. Who is familiar with the pruning? No one? Who is familiar with pruning? No one? Pruning is very, very important and simple strategy for the AI. This means ignoring from some portions of the game tree without losing the good result in the final decision. To ignore from some portions of game theory, you should guarantee to limit the influence of the pruning on the final decision. By using pruning, you can improve the speed of your algorithm. And instead of checking the tree in deeper layers, you can receive the optimal solution very, very, very simply. To sense about the pruning, let's consider this example. Maybe you have a job with $10,000. When the salary is $10,000 and you evaluate other jobs, assume that there is a proposal for you to get job B. But the salary of job B is $8,000. In this situation, you compare the salaries because the salary of the job B is less than the salary of job A. You don't explore the job B. Really, you pruned the evaluation of job B because the salary is less than job A. This is the meaning of pruning. In the pruning, when you have an opportunity to check a new branch whose benefit is less than the accessible brand or accessible utility, you stop from expansion. This is the key point for improving the quality of searching on game tree. For example, we started from this max node. This max node consider the leftmost child. The leftmost child is mean player. Mean player consider the leftmost child. The leftmost child is a terminal node with utility 3. 3 is returned to mean player. Mean player take it and check the next child. The next child is another terminal node with 12 utility. Mean player compares 3 with 12 because mean player tries to minimize the utility. It consider 3 again. And for the next expansion, 8 is compared with 3. Again, 3 is better for min player. Because of that, min player returns 3 to its father. The father checks the other successors. The middle successor is again min player. Min player calls the terminal node. Terminal node is 2 returns, but 2 is less than accessible utility. Accessible utility is 3, but min operator receives 2. Whether or not the other branch return more utility, because min player minimizes the output of the child, it returns at most 2. But max player, because from the middle successor cannot get a utility greater than 3, it stops from branching and prunes the other childs. But for the final successor, because the first child is 14 and 14 is better than 3, we continue the search. The second successor is 5. Minimum is over on 14 and 5, returns 5. Again, 5 is better than 3. We continue without pruning. The last one is 2. The minimum over 14, 5, and 2 is 2, because 2 is worse than 3. The max player does not select this action for continuing, and the searching stops. As you see, the search stops without considering some parts of the tree because of the pruning. This is the meaning of pruning in min-max. Do you understand? Do you understand the process? Yeah? Do you have any problem?
No, Doctor.
No.
Merci.
Thanks so much. Now, we can implement alpha-beta pruning. As you see, we have 2 players, max player and min player. Because of that, we need a bound for max player and a bound for min player. Assume that alpha is used for the limit for max player and beta is used for min player. Because of that, we define alpha-beta pruning. Alpha-beta pruning. Alpha-beta pruning contains 2 versions. One version for min player and one version for max player. In this slide, I explained about the min version. As you remember, in the mean player, we call mean value function. Consider n as the mean player. It calls mean value over the successor. The successor of n are maximum player. Because of that, we need to estimate the output of the n's children and getting the minimization over them to find the best decision for mean player, because the children of n are max. The max player check their value with respect to alpha, and if the alpha as the best value of the max player is better than the corresponding alpha, we can prune the tree. This means n compare the received value with alpha. If n receive a value worse than alpha, because the above node is max player, the mean player know that such branch is not allowed by max node. Because of that, checking the next steps is not necessary. Come back to previous slide. It is mean node when the node gets 2 as the output of the node, because 2 is less than 3 and the above node is maximized, and max player chooses the action for the next step, the max child does not allow the corresponding action to receive to a value equal to 2 or less than 2, where 3 is accessible by other branches. Because of that, it terminates the branching. This is the meaning of stopping consideration of other children of n when n becomes worse than alpha. Similarly, we can implement the same version for max child. To present the code, first to the max child best option at the initialization phase, because there is no option to continue, we consider alpha equal to minus infinity. And also beta refers to best option for mean player at the first. At the first, because there is no option for mean operator, it consider beta equal to positive infinite. And again, we have two box, blue box for max player and red box for mean player. In both of the definition of max value and mean value, we enhances the performance by augmenting alpha and beta in the arguments. All of this window is defined by recursive function with respect to alpha and beta, which are updated by max player and mid player. And when the terms is max, the max player started the selection, it considered the different actions and movements and select an action with the highest value movement. Because of that, it tries to call a loop over the successor. In this loop, the successor, because the successor are mid player, the mean value of the successor with respect to alpha and beta are as you see in step 1, we check that if the receive node is terminal, there is no necessary to continue the searching process, and because of that, we return the utility value and stop. Otherwise, in step 2, we initialize v equal to minus infinity and try to improve the value of v. In step 3, we have a loop over the all children with respect to different action. Because we focus on the max player in this slide, we know that all of the children are mean. Because of that, we define a loop over the different actions. With respect to any action, we access to a child. The child is mean player. Because of that, mean value is called. But instead of sending just child as the argument, we augment alpha and beta in the list of arguments of this function. The mean value try to process on a pass and returns the value, and we compare this value with the current V. If the returned value by the mean value procedure is greater than V, we update V. Otherwise, we ignore from this value and consider the next. When V is updated, we check it for pruning process. In the pruning process, we check V. No. Please pay attention. Very, very important. V is checked by beta. Beta is the or we need to check V with beta because the father of any max player is mean player. Because of that, we need to check this option of
You are now muted.
the corresponding action. Please pay attention again. I explained again. If V is greater than beta, because the father or the above node is mean player. Mean player has an option with beta value. It check V with beta. If V is greater than beta, the mean player think that this branch is not useful for myself. I have a better option with a beta value, and my current option beta is less than this successor. Because of that, checking the behavior of this successor is not useful for myself. Because of that, mean player causes to prune this branch. And we say that if V is greater than or equal to beta, we can prune the node. The value of V just found is already greater than the accessible beta for min player. Because of that, the min player whose turn is the above of this node does not allow to take this action, and because of that, continuation of the searching is not useful and we stop. Otherwise, if we come strictly less than beta, then we can update the alpha because we have a better option instead of the previous one, and we can update the alpha as the maximum of alpha and v. When maximum of alpha, current alpha and v is v, this means that a better option for max player is defined and is obtained. Because of that, we update the alpha limit for max player. Similarly, for the min player, we call mean value with respect to the state and to parameter alpha and beta. The main job of this node is to get the lowest value and selecting an action with respect to lowest value, and in this process it tries to decrease the utility of max player. The details of the algorithm is given here. As you see, in step 1, we check similarly the terminal nodes. If we receive 2 terminal nodes, we do not need to search more, and the game is over, and we return the utility value. Otherwise, if the node is not terminal, we initialize with positive infinity, and we define a loop over all of the actions and all children. The children are mean. Because of that, we try to call value over the children. In the current node, we get min operator over the current v and the return of the successor. This is the return of the successor, max value, but v is the current value. If the minimum is v, we have not any change in the v value, but if the minimum of v and max value is less than v, we update v. In this case, we consider the process for any max value, max player as the child. And for pruning, check v with alpha. Why we check V with alpha? Because the father of any min player is max player. Because of that, the max player consider V and compare it with its option. Alpha is the option of the father. If V is less than alpha or equal to alpha, the father say that I do not allow to select the corresponding action for the next step. Because of that, searching more in the child is not necessary, because the father does not permit to choose this node for next step. And we prune the tree. Otherwise, if V is strictly greater than alpha, now we have a chance for checking the states. We compare the received V with beta. Beta is the best option for the min player. If V is greater than beta, the min player say that it is not necessary to update. I have a better option for beta. But if V is less than beta, the min player is interested to update beta and update beta with V and continue the process. This is the implementation of alpha and beta pruning. As you see in this example, in state A, we started from minus infinity and positive infinity as alpha and beta. We checked the leftmost child. The leftmost child is again min player. It checks the leftmost child. The leftmost child is terminal node 3. 3 is less than positive infinite. Because of that, it update the upper bound 3 and check the next child. The next child is 12. 12 is greater than 3 and beta is not updated. Again, check the third option. The third option is 8. 8 is greater than 3 and we don't update beta, but because the minimum of 3 childs is 3, we can update the alpha value for the father. Alpha value is updated as the 3. Now the second child is checked. The second child is middle one. The leftmost child is 2. again update the beta, and beta equals to 2. Max player in the above check the accessible utility 3 and 2, because 3 is better than 2. The pruning is done and the next child is not checked. For the last successor, it consider the rightmost child. The rightmost child check the children. The first children is a terminal with 14. 14 is better. Because of that, it updates the beta value. 14 is better than 3. Because of that, the pruning is not usable, and we need to check the next. The next child is 5, and still 5 is better than the 3. We continue the search. The last one is 2, and the value of 2 is returned to the mean operator. The mean operator gets the mean over 14, 5, and 2. 2 is received, but because 2 is less than 3, we cannot permit to choose the corresponding action, and the algorithm terminates with 3. To show the details, as you see, the max player calls the root. Root has 3 successors. All of the successors are mean operator. Because of that, we use mean over the successor, mean over the successor, and mean over the successor. For the first one, the successor is 3, 12, and 8. For the next, we get minimum over 2 and others. X and Y are others, but because 2 is less than 3, the others are pruned. But for the last one, 14 and 5 are better than 3. Because of that, the pruning is not done. And we check all of the successors between 14, 5, and 2. 2 is selected, but 2 is less than 3. Because of that, we consider the maximum over 3 and 2. 3 is better, and we stop with 3. Do you have any question about the process, about the alphabet pruning? No question? Perfect. But the pruning is dependent of the order of the nodes. If we use a naive version of the alphabet pruning, sometimes there is no effect on the computation time. For example, as you see in this example, at the first we received to 10. In the second node, we check again 10, and last we check 0. But if the order of the node are defined better, the algorithm may be implemented efficiently. Because of that, perfect ordering is important for alphabet pruning. In the previous example, if the order of the last node is 2, 5, 14, we can prune 5 and 14 from the process. But because the order is 14, 5, 2, we cannot use the efficient alphabet pruning. But finding the perfect ordering is hard, but it is possible to check it by a complexity big O, B power M over 2. But the search is very, very great. In this situation, the meta learning is useful. What's the meaning of meta learning? Meta learning is simply think about think. When you try to thinking about thinking, you can improve the quality of games. Meta reasoning is very, very important in all kinds of the algorithms in AI. In this paradigm, instead of searching the best movement and finding the best action, the algorithm decided to the fundamental concept of how it should search the best movement. This fundamental problem is related to allocate the restricted computational resource to the location that are needed. This is the meaning of saving process and saving resources. For example, sometimes in a game, for example, in the chess, you face with some stable and simple states. We refer to these states as the quiet mid-game. In the quiet mid-game, you change the location of the states, but there is no important effect on the problem. Otherwise, some actions are very, very important, and they can violate the problem. For example, you have a tactical sequence that causes a great benefit or a great loss in the game. We refer to this state as the violated state or sharp state. Meta reasoning is recognizing the stable and violated states and allocating more power on analyzing the sharp or violated or more complex states. And this is very, very important for making a strategy for searching. It is a dynamic or adaptable process. In these cases, you need to define the benefit and cost for your action. The cost is dependent on the, for example, CPU cycle. The CPU cycle for expanding a particular branch of the tree is defined as the cost of any action. And the benefit is dependent on the amount of improvement in the decision quality. This is important for estimating the probability of win or loss. Now, meta reasoning tries to maximize the benefit of the search with respect to the corresponding cost. For example, iterative deeping is a kind of meta reasoning because instead of DFS, you check the first depth. If the goal is not defined in the first level, you extend your attention to the depths 2 and depths 3 and so on. But sometimes we need to improve the quality of meta reasoning based on some information about the depths to guarantee to find the optimal solution. And finding the solution in the earlier steps. In this situation, you may combine the alpha-beta pruning approach in this process. For example, in some cases, you allocate more attention, for example, 18% of your power for checking some complex attacks in the checkmate, and 20% of your power for analyzing the quiet movements. In this situation, you improve the quality of searching by meta reasoning. In the next session, we discuss and the meta reasoning in the games, and we try to improve the quality of adversarial search by considering different kinds of meta reasoning. That's okay. I'm ready for your question. If there is any problem or drawback. No question? I explained in the first part of the class about uploading the necessary material in the courses. I uploaded the slides in the courses. Please read it very, very carefully. And in the next session, we discuss more on meta reasoning to improve the quality. Mr. Kazem, do you have any question? No?
No, Doctor.
Hope the best of the best. I hope you enjoy from the adversarial search and this kind of the improvement. In the next class, we discuss deeply on meta reasoning. Have the best of the best. Goodbye.
Goodbye, Doctor.
Goodbye, Doctor.
Thank you, Doctor.